So we make things small. And some of the materials that we make small, especially if they have crystalline structure, they show something where their electronic and optical properties are different at that small scale, especially below 10 nanometer. And that phenomena is something what we call as quantum confinement. We don't, it's not that we make something small like quantum dots, we make 20 nanometer and we are pumping them. No, we make them to that scale. And we do, many times it's bottom-up assembly. It's where we have recipes, we mix things and we create those, maybe it's a zero-dimensional structure, which would be a quantum dot. Now here you see I've written 3D confinement, but the material is zero-dimensional. So don't mix those things, but see the perspective where we come from. A quantum dot is a nanoparticle. It's just a very small particle which has very small dimension in all 3 dimensions. Very small size in all 3 dimensions. So we call it a zero-dimensional material. But when it is zero-dimensional, which means its electrons or photons associated to that are confined in 3 dimensions. They cannot go in any dimension. So it's 3D confined. Getting me? It's a 0D material, but it's 3D confined. And then we have quantum wires, which are 1-dimensional because thickness is almost negligible with respect to the length. So it's a 1D material. But in this now, there is 2D confinement. They are only allowed to go in one direction, which would be along the length of the wire. So we call it 2D confinement. And then there's 3D materials where we would say a 2D material, sorry, which would be like graphene, which is, you can go anywhere in 2-dimensional. So it's 1D confined. So what happens when we do that? Basically, we are now interfering with the electronic band structure of the devices. Now, this is a slightly advanced concept, but nevertheless helps us. I saw some of you, they wanted to learn more. Now, when we have this, and then there is a bulk material, 3D, where all carriers can go everywhere. And we have explored these in last decade or so, where we have now many new uses of these materials. So these 2, 1 or 0-dimensional inorganic materials. Inorganic, they're not carbon-based, but there are other materials, but they're crystalline structure for most part. They represent a bridge between molecular catalysis and the high performance and stability of these materials. So we do reactions and we come up with these very stable materials. And they show electronic or optical properties because of confining electrons in those directions, in whatever the case, 3D confinement or 2D confinement or 1D confinement. And that the physical phenomena where we are restricting them in going in those is what we call as quantum confined structure. And these structures are, they show interesting properties. And those properties come from the idea of density of state. So in a semiconductor material, unlike conductors, so conductor, we take metals to be conductors, but conductors. So conductors, electrons can go in any direction. You turn on voltage, they start flowing. But semiconductor materials, they cannot just start flowing. So in semiconductor materials, two conditions need to be met. There has to be free electrons that we can pump energy and they can jump from valence band to conduction band. That's one condition. The second condition is there should be energy states available in conduction band, which they can fill, and then they should be able to transport. Is any of you taking the solid state device course with me as well today, before this class, or has taken it before? I think some of you have taken solid states with me.
Yeah,
So
I took
we
it last semester.
so we talked about valence band and conduction band, right? So they have to jump and they have to get to the conduction band, and in conduction and band there has to be free energy states that they can fill up, and then they will be available for conductivity. So we use a statistical function to find density of states. So that presence of density of states is an exponential function. So what's shown in 3D material, that yeah, you have higher energy, you go away from conduction band, you have exponentially high number of density of states, and then they fall down. So you have very close to conduction band, many states are available. Now, when you confine these materials, we are confining the states that are available for those materials. So much so that in 0D material quantum dot, there is only two states available for them. So from valence band, they can go only to one other state in conduction band. So what we have done, we have physically confined those. So now when the electron would jump, or electron would go from conduction band to valence band, it's going to emit only one wavelength because it is coming through a well-defined change in energy. Unlike 3D material, where there are a bunch of density of states, so electron may be coming from other energy states, hence giving other wavelengths as well. But in quantum dot, it can only emit one wavelength because the states are very well defined, because we have restricted physically for that electron to have multiple states. Now, there's very involved physics, but there are simple approximations that are done in common solid state device expressions, where we uh, then take care of band gap problem, absorption coefficients, and density of states in what we call low dimensional materials. So there is a thing called time-dependent Schrodinger equation, which basically takes care of the interaction between light and electron. But for quantum confined systems, though many of the parameters that go into solving that equation, they are which are taken constant in bulk semiconductors, are now made dependent on the dimension of the material. Hence, the solution of those uh, these Schrodinger equation becomes different, and the band gap edge position, and the density of state, they all change due to the quantum confinement of those smaller, low dimensional materials, as they are shown here, right? So this figure that's gone, it just shows that symmetry is broken. It's not just a exponential function. Now it becomes a step function. Then you have just two values for 2D confined material and just one value for conduction level for 0D material quantum dot. And hence then uh, we restrict the levels. Instead of having many density of states, we have to deal with just one density or just one state. All right, a little bit primer on that. You could see my slides. All right, so that was on quantum confinement and what happens when we have uh, those material. So today I wanted to get into on a few nanomaterials which are used for many bio applications. And if we look at how they are made, how they're built, that can help us see that the nanoscale properties that are used from those things and what goes into making those materials at that scale. Just a never-ending uh, hallway. So let's start with nanomembranes or nanoporous membranes. There are two types. We use them polycarbonate membranes or alumina. Alumina is aluminum dioxide. We have aluminum, we make aluminum dioxide from that. What we get is when there is a special way how we do oxidation. So it's called anodization, which is if you know electrolysis, you use one electrode, the cathode and anode, and then we add some uh, ions to the solution and we get them to deposit. So that's how the batteries work, 12-volt battery or any battery with liquid that works like that, right? So what we do is we use that kind of method to create uh, so many things. We can create polymers, films of polymers with very well-defined holes in it. We can make fibers. We can make, so the idea is we use that process to create this well-ordered structure, like shown here. It's called porous anodic alumina, or it's just aluminum oxide or anodic aluminum oxide, AAO or PAA means the same thing. What happens is that during the process of oxidation, it creates a very well organized structure, which is like a honeycomb structure. You know, like the honeybees, they make this structure with well ordered thing. So this formation of anodic alumina gives us a very highly organized 3D structure with 2D hexagonal pores in it. And this has been around for more than 30 years. So what we did was then we took that and we used that as a template to make nanowires, to make many different nanostructures. So you have this, if you see the lower picture, that's showing some cross section of that honeycomb structure, which shows very well organized nanoscale cylinders in it. And that has been used to do many things. We have used them to fill them up with uh, elements, gold, uh, so many different things to create nanoscale forest of nanowires. This particular example is just showing placing gold particles or gold dots in a very well organized structure. And what we do is for that structure, we'll look at example of nanowire synthesis. So you can make nanowires at very precise location on the surface of a wafer. So we make porous alumina with anodization with that electrolysis process. You remove alumina, you can etch it, you get this, the surface at the bottom, which has very well-defined structure. You grow it again with second anodization, and ultimately you deposit metal. In this case, we are doing the gold evaporation using that alumina as a mask and getting those layers. So now these porous structure is electrically insulating. It is stable. We make the picture like it's a very well defined structure, but yeah, it is close enough. But and you can, depending on how long we do the electrolysis, we can control the inner tube size from 4 to 250 nanometer. We can control the density of how many do we want out of that. And that is kind of gives us a structure that has been used to create nanowires. Or this Nordic alumina itself has been used as what we call as nanoporous membranes. So nanoporous membrane or nanomembranes is something which has been used to separate many biological entities, has been used to do what we call filtration. So filtration, we know in larger terms, we know filtration is a process where we separate out things based on their size, right? So if you have a liquid, we filter it, we remove things. But here at nanoscale, we can use them as active filters like ion channels in cells, or ion or channels which are there, nuclear pore channels. So there are, in living things, there are small holes which can selectively push through specific chemicals. So these kind of things have been done where people have created these membranes with nanoscale channels in it and have used them to do molecular separation. There's an example showing the alumina has been uh, just chopped off at some places, and they're showing uniform length of those channels. So the other type, polycarbonate membrane, is there's you can buy them commercially. So these are also something where we can, but in this case, it's not the anodization process. It's where they throw ions at a membrane, and those ions can uh, etch and leave a track in those membranes, and they have been used to do that. So now these membranes have been used to template synthesis, many other materials with that. Micro and nano level size of cylindrical things, or they have been used themselves as channels itself. So here's one example where what they did was they used that kind of membrane to make self-assembled monolayer of DNA molecules inside, and then they did kind of an active filtration. So in this case, what they did was they put a bunch of molecules of DNA on one side, but after some time they saw that on the other side, there was the molecules which could bind with that DNA molecule. They say much more higher concentration of those on the other side. So it can be used kind of to separate out different molecules based on their interaction with the SAM inside a channel. They've used this to, again, like before I was showing, they can place gold particles at specific places. They have used that to grow forest of things at very specific locations. Like here it is showing they covered everything, and then they removed at some places, and then they got nanowires made only on those specific places where they, so you see, that's a side view, you see that membranes, not the membranes have been used to grow these nanowires out of that place, only on selective places. They've used this to fabricate zinc oxide nanowires as well. So here's another example where they have grown a forest of nanowires. So some of you in GRP, they were talking about how can you make these things at mass scale? For example, there was a question about graphene, there was a question about carbon nanotubes. So these are the kind of approaches they use where they can template things out, and then they can grow, like in this case, nanowires in a very precise order, in a very precise size, at very precise locations. And those can be used to do whatever you want to do. You can break them apart from the surface. So you can have a solution where all those nanowires are floating, free floating in a solution, and can be transferred on the chip. Now, nanowires is another area where lots of biosensing work has been done. And like this example I was showing where they could place a gold particle at a specific place, that is one way, that's the first step in creating nanowires, and we'll talk about that here. So what we do is we place a, a what you call a particle at a specific location. In this case, on a silicon substrate, we have put down a gold particle. And if we heat it up, the gold is molten, it's just staying there, and we put the silicon vapor into that chamber. So this process is called VLS synthesis, vapor liquid solid synthesis. The silicon gets absorbed into the gold. It there is a process where they make an alloy with gold, and the silicon travels to the interface of gold with the silicon and on the wafers and the substrate, and starts accumulating, starts creating kind of a crystalline structure at the interface. So that crystalline structure, or that binding of silicon at the bottom interface, results into formation of a nanowire. So it's kind of you take a brick by brick and So you would put down, if you think of it, I would put down bricks and I would keep on climbing on top of the bricks and I can make a tower and I'm sitting at the top of that tower. So it's the kind of thing where that gold particle would absorb the vapor and the silicon would travel by diffusion, by random transport. Once it finds the interface, which is colder than the hot metal, it would start forming a, a structure which would follow the crystalline structure of the silicon substrate. This is one of the earlier ways how silicon nanowires were made. Now we have come a long way and we use this a bunch of materials. This is a thing called phase diagram. People who do material science, they use phase diagram of many materials. So what you can see on the x-axis is the percentage of silicon absorbed into gold, and the y-axis is the temperature. So when you have at a specific temperature, the increase in the the what do you call the silicon that gets absorbed into gold, as it cools down, it travels from A, B, C, D, and from liquid, it becomes a solid. So this kind of a phase diagram, which shows the first the gold is deposited as a catalyst, and then it forms an alloy by reacting with the vapor silicon. On the C, this nanowire nucleation starts. So the word that we use here is nucleation of a nanowire, which is the silicon getting to the surface and forming a shape and ultimately coming out as a nanowire. So this is very early way how this VLS method was used to create nanowires. But now we create nanowires in many different ways. We use catalytic growth by using laser, where you would melt only that part and you would move the laser and it can start, the atoms can start building up and creating a wire following the track of that laser. There are ways where we can lay out polymers and let polymers follow a template. So in this case, they're showing nanowires synthesized by one material, by two material, by alternating two materials. So these, what we can get is we can get polymers to create nanowires, and in the polymers we can incorporate biomolecules. We can incorporate DNA. We can incorporate proteins in it. So in that polymer, we can add nanoparticles, magnetic nanoparticles, conductive nanoparticles, quantum dots to get many wide range of properties, magnetic, optical, electrical. So we use now nanowires with many, many different reactivities, properties, physical properties, electrical properties, and those can be used now to bind and detect biological molecules. For example, there's one of the very earlier report from 2001, where they showed that nanowire transistor could be used to detect few copies of a biomarker, few copies of a protein molecule. So what they did was they functionalized nanowires and they were measuring current across, and they would see the transduction effect, which is transducer. What happens in, sorry, transistor effect, where the binding of a protein molecule would result into change of charge in the nanowire, and hence the conductivity through the nanowire would change. So here, if you look at this picture on the right-hand side, what they're showing is that G is conductivity in nanosiemens. So that would change when a liquid with specific molecules would be added. They would see change of conductivity going up and up in real time as the fluid was, as the molecule or whatever the biosensor as it was introduced, that would change the conductivity of the nanowire. So this is just few examples of where nanomaterials have been used to create nanosensors. So in this case, uh, another case where they created many nanowires in parallel, that's shown on the left-hand side. And each nanowire was functionalized with bioreceptors, and they would find or they would detect the presence of the molecule when it came in contact with the nanowire. And the right-hand side is showing that electrical conductance change again in nanosiemens, where the binding is shown as reduction or increase of the conductivity, right? So they have shown these for so many applications as gas sensors, as toxic material sensors, as uh, viral load sensors. So especially with polymer nanowires, we can achieve many different kinds of uh, activities with that, because polymers is easy to then incorporate molecules with that. All right. So few examples on nanomaterials and how we can make them and how we can interface them with things in the living world.